All right, let's just jump right in. Balancing chemical equations. I know for some of you it's kind of like a fun puzzle, but for a lot of us, it can be a total headache. What if I told you it's less about some crazy abstract math and way more about telling a true story? Well, in this explainer, that's exactly what we're going to do. We're going to crack this code together. And hey, if you've ever felt like this student on Reddit, trust me, you are not alone. It can seriously feel like those numbers just materialize out of thin air. But I promise you, they don't. There's a really clear, simple logic behind it. And by the end of this, you're going to see exactly where they come from and, more importantly, why. The best way to think about it is like a recipe. An unbalanced equation, that's just the ingredient list. It tells you, hey, hydrogen and oxygen make water. Cool. But a balanced equation, now that's the actual recipe. It tells you the exact amounts, the precise proportions you need for this thing to actually happen in the real world. I love this way of looking at it. A chemical equation isn't just some boring formula on a page, it's a story. It's the story of what atoms we start with, what crazy dance they do, and what they end up becoming. And balancing the equation, that's just us making sure the story we write down on paper actually matches what's happening in reality. And every good story has rules, right? Well, chemistry has one huge, unbreakable rule, the law of conservation of mass. You can't just lose an atom along the way, and you definitely can't create one out of nothing. Every single atom you have on the left side, the reactants, has to be there on the right side, the products. They might be rearranged, but they're all there. This is why balancing isn't just a suggestion, it's the law. So how do we actually do it? Well, like any game, you gotta know the rules. And the rules for balancing are surprisingly simple once you get the hang of them. So let's get into the nitty-gritty. And here it is, the golden rule. If you remember one thing from this whole explainer, make it this. You can only change the big numbers out front of the molecules. We call those coefficients. They just change how many of that molecule you have. You can never, and I mean ever, touch those little numbers within a formula. Those are the subscripts. Don't do it. So these are the classic traps people fall into, changing those subscripts, trying to balance the easy stuff first, which can actually make it harder, forgetting to do that final check at the end, or, breaking up little groups of atoms that like to stick together. We're going to make sure you sidestep all of these. This right here shows you exactly why that golden rule is so critical. Say you're trying to balance our water equation. H2 plus O2 gives you H2O. You see, you need another oxygen on the right. You can't just change H2O to H2O2. Why? Because that's not water anymore. That's hydrogen peroxide. You've created a totally different substance. The right way is to put a big 2 in front of H2O. That just means you have 2 molecules of water. See the difference? You change the quantity, not the identity. Okay, theory's over. Let's put this into practice. There's a simple method, sometimes called atom accounting, that turns this whole thing from a confusing mess into a really straightforward checklist. Let's use our water example and walk through it. Okay, step 1. Count everything up. On the left, we've got 2 hydrogens, 2 oxygens. On the right, 2 hydrogens, but only 1 oxygen, not balanced. So step 2, let's fix the oxygen. We'll put a big 2 in front of H2O. Now our oxygens are good, 2 on each side. But wait, now we have to recount. That 2 in front of H2O gives us 4 hydrogens on the right. Whoops. But no big deal. Step 4, we just go back to the left side and put a 2 in front of the H2. Now, let's do our final check. And would you look at that? 4 hydrogens on the left, 4 on the right. Check. 2 oxygens on the left, 2 on the right. Check. Every single atom is accounted for. The law of conservation of mass is happy. And that equation is perfectly balanced. See? Not so bad. Now, this method we just used, balancing by inspection, it's going to work for like 99% of the stuff you'll run into. But just so you know, when things get really, really messy, chemists have a few more powerful tools in their toolkit. Yeah, you can use algebra to set up a whole system of equations and solve for the coefficients. You can break down really complex reactions into simpler half reactions. There are even computer algorithms that use some pretty cool math. But honestly, they all build on the exact same fundamental idea we just covered. And I think Dr. Carl Thursk puts it perfectly here. Hearing words like algebra mixed with chemistry might sound like a nightmare, but it's really not that bad. As long as you have a system, a step-by-step approach, you can tackle anything. So why? Why did we just spend all this time on what feels like a classroom exercise? Because balancing equations is not just about passing your next chem test. It is the absolute bedrock for building a cleaner, more efficient world. And that brings us to this awesome concept from green chemistry called atom economy. It's a really simple but powerful idea. Basically, it asks, of all the atoms you put into a reaction, how many of them actually end up in the stuff you want to make versus how many just become waste? Obviously, the higher the atom economy, the better. And here's the kicker. You literally cannot calculate atom economy without a balanced chemical equation. It's impossible. Those big numbers, the coefficients, tell you the exact ratios you need to figure out how much product you get and how much waste you create. It all starts there. Let me give you a fantastic real-world example. Ibuprofen. We all have it. The original way they made it back in the 60s was, well, messy. It was a long, 6-step process that created tons of waste. But then, in the 90s, a company developed a new, much greener process. It was shorter, way more efficient, and got most of those starting atoms into the final ibuprofen molecule. And, I mean, just look at the difference. The old process had an atom economy of only 40%. That means 60% of all the starting material was just waste. The new green process shot that up to 77%. It nearly doubled the efficiency. And that whole revolution in thinking started with chemists looking at the balanced equations and asking, can we do this better? So you see, this one little skill that we learn in chemistry class has these huge ripple effects. It impacts everything, how we use raw materials, how much pollution we create, and ultimately how sustainable the things we make are for our planet. So I'll leave you with this thought. We changed the recipe for ibuprofen and made it twice as efficient. What other everyday chemical recipes are out there? For plastics, for fuels, for fertilizers, just waiting for someone to come along and figure out a better, greener way to balance the equation. It really does all start with cracking that code.